Hello, AP Calculus students, Mr. Ford here with a homework tutorial. I'm going to go kind of fast because I got 15 minutes. I'm going to see if I can squeeze this one in. Just trying to catch up on work here. This is for 8.1.1. This is our first lesson dealing with three-dimensional revolutions, but we have a lot of review on here too, so we'll keep it up going forward. 8.4 is really reviewing what's going on here. When you talk about this big sigma notation, it looks confusing, but when you think about f of x, or really f of anything on this thing, what this is telling you is just the height of the rectangle, and the delta x is telling you the width. So dx is the width of the rectangle, and f of x times dx is the height times the width, which in other words tells you the area of each rectangle. And this is how we can approximate, amorphous shapes like this by cutting them up into very, very small rectangles and adding all of those up, which is what an integral does. 8.5, sketch the region bounded by the curve f of x equals square root of x and the x-axis for 4 to 9. So we'll go ahead and do that. That's actually really easy to do by hand. We don't need to use a calculator necessarily for it. Since 1, 2, 3, 4, the square root of 4 gives you 2. So there's a point right there. And 5, 6, 7, 8, 9 gives you 3, because the square root of 9 is 3. And so the curve kind of looks like that right there. And there is your area that we're looking for. That's kind of what we're looking for, is that blob right there. Draw a typical rectangle in the region and describe how the height and width are determined. So a typical rectangle would look like this. You just kind of like put one rectangle in the middle and then kind of pull it off to the side and think about it. This is for part B. So the width and length of that rectangle. The width we're just going to call dx, since we always call it that. And the height of it, honestly, is just found by doing whatever f of x is, which in this case is the square root of x. The height of that rectangle is just the square root of whatever number that we're at is. Question C, set up and evaluate an integral to calculate the area of the region. We're going to do this one calculator free because we totally can. So if we're going to add up all of those rectangles, this would just be the integral from 4 to 9 of the square root of x dx. That's it. And this is actually really easy to evaluate since the square root of x is just x to the 1/2 power. So this is the square root, or the integral from 4 to 9 of x to the 1/2 dx, which we can evaluate by doing the antiderivative, which would be x to the 3/2 power times 2 divided by 3. Since that way when 3/2 comes down, it'll multiply out with 2/3 and cancel and drop down by 1 to become x to the 1/2. We don't need a plus c in this one because we're actually going to evaluate it by putting 9 and 4 into our x value and figuring out what that is. So 2 times 9 to the 3/2 power over 3 minus 2 times 4 to the 3/2 power over 3. And don't panic too much on this. To the 3/2 power, you can do the 1/2 power first and then the 3rd power. And the 1/2 is just a square root. So this would be 2 times 3 to the 3rd minus 2 times 2 to the 3rd. And they're over 3, like that. So that becomes 2 times 27 over 3 minus 2 times 8 over 3. Which is going to be 54 over 3 minus 16 over 3, which is going to be 38 over 3, and that is not a whole number, so I'm going to leave it as 38 over 3, and that is my answer, and I'm sticking with it. If you want to use a calculator for that, you certainly can, but I don't think you need to for this problem, and that would be kind of a fair game for the calculator-free portion of your AP test. For question 8.6, we got a bunch of derivatives to do. These aren't super pretty clear, so on this, but I can look them up on the old website, so that's what I'm going to do here. So for question A, we're going to do a lot of work for this one. This is going to take a little bit of time here. This might become a two-part video depending on how much time is going on here, but we'll see. I don't want to go too fast and leave people in the dark here. For question A, we're looking for the derivative, the d dx, of the 3rd root of 5x squared minus 17x. Or, what I like to say is, I would write this as 5x squared minus 17x to the 1/3 power. Whenever you can think about it like that, it makes your derivatives easier because you can just use the power rule. So our derivative will be 1/3 times the original inside 5x squared minus 17x, all raised to the negative 2/3 power, because when you drop 1/3 down by 1, it becomes negative 2/3. Of course, that's not done yet because we still have to think about the chain rule. How do we have to multiply by the derivative of the inside part, which would be 10x minus 17. And that is, I believe, the correct answer. And I'm not going to go any further than that because I wouldn't need to in any capacity. I suppose if you really wanted to get fancy with it, you could do 1 over 3 times the third root of 5x squared minus 17x squared times 10x minus 17. I guess you could slap 10x minus 17 on the top of that fraction too. If you wanted to get fancy, you could. You don't need to, though. Question B is going to look really complicated at first. We're looking for the derivative of two polynomials multiplied together, 4x to the third plus 2x minus 5 times 8 minus 7x to the third. And while you can use the product rule for this, you can, I would not recommend this, since it's easy enough, I think, to multiply this all the way out. This would instead be the derivative of, and let's just get our thinking helmets on, 4x to the third times 8 is 32x to the third, plus 2x times 8 is 16x minus 40. And then we'll do the minus 7x to the third one. This would be minus 28x to the sixth, minus 14x to the fourth, plus 35x to the third. Just multiplying all those things out, multiplying everything by the 8, and then multiplying everything by the 7x to the third. I color-coded my answers, too. The purple ones are the 8, the orange ones are the 7x to the third. Now, it's just a chain of product rules, power rules. I suppose you could combine together. There's 2x to the thirds there. I'll do that later. So 32 times 3 is 96x squared plus 16. That's 0. This one goes away. Minus 12, blah, blah, blah. I was hoping to avoid using a calculator, but 28 times 6 is going to escape me. 168 x to the fifth minus 14 times 4 is 40 plus 16. 56 x to the third plus 35 times 3, which is 90 plus 15, 105x squared. And again, I suppose you can combine these two together because they are the same term. So 105 plus 96 is going to be 201. So if I put it in order, I'll have negative 168x to the fifth minus 56x to the third plus 201x squared plus 16. That is my answer, and I'm sticking with it. Did I miss one? No, I combined them together. That's good. I like that answer. It's pretty good. You could debate whether this is faster than just using the product rule, and the product rule might look a little different when you're all done, but I promise you that if you work it all the way out, it'll be the same. Question C. Oh, I'm going to run into my other work from another problem, so I'm going to keep going over here. Question C is going to look like this. We're looking for the derivative of the sine of x, which is a pretty cool little thing. I guess it's sine. Oh, you know what? There's a trick in this problem. Look at this. It's the sine of t. This is a different variable than x. If I'm reading this right, x and t are different variables. So the derivative with respect to x of this thing is going to be 0, because the sine of t is just a constant. I'm going to check the answer on this one, make sure I'm thinking about this right. No, they want that. That's just a typo on their part. Okay, they want the derivative with respect to t. Okay. See, here I was thinking that they were trying to pull a fast one on us. No, they should. It should look like that. They do want the legit derivative of this, so we'll go and do the legit derivative. All right, so we got to do the derivative of the outside part first. So the derivative of the sine is the cosine of the original inside, sine of t. But of course, we're not allowed to just leave that as it is. We got to do the derivative of sine next, which is the derivative of cosine. Or sorry, the derivative of cosine is also. Oh man, I'm saying a lot of words here. The derivative of sine is also cosine. So I believe that this is the correct answer. Cosine squared. No, cosine of the sine of t times cosine. You can't square those cosines there. They're not the same thing. I believe this is the correct answer right there. I am going to check. Again, I'm going to check my answer tab here and make sure I'm right before I move on. Hey, okay, good. And our final problem here, question D, which is, again, going to look complicated, but actually it's really simple if you think about it. Because it's the derivative of an integral. It's the d dx of the integral 7x times the cosine of x of the natural log of t squared dt. So all that's going to happen here is when we take the derivative, you know, the fundamental theorem of calculus says that the derivative and the integral are opposites of each other, so they're going to pretty much cancel out. What we need to remember here is that we do have to think about chain rule. So we're going to treat this like a fundamental theorem of calculus. What we're going to do is the antiderivative, and then we're going to plug in, not even the antiderivative, because the antiderivative of this is just going to cancel out. So it's the natural log of something squared. However, since we do have a top and a bottom bound, we do have to plug in our top and bottom bound. So this will be the natural log of the cosine squared of x minus, I'm leaving some space here, the natural log of 49x squared, which is 7x squared, like that. Of course, remember that we can't just plug those numbers in. We also we're taking a derivative, so we also have to think about the chain rule here. So we need to multiply by the derivative of cosine squared, which in this case is going to be another complicated thing to do. Or no, oh sorry, not the derivative of cosine squared, just the derivative of cosine, which is negative sine. And we need to multiply by the derivative of 7x, which is just 7. So your final answer is going to be something like the negative natural log of the cosine squared of x times sine of x minus 7 natural log 49x squared. Like that. Kind of cool, kind of not, I guess. I don't know. All right, let's go on. This video is going to have to be a two-parter, I think, because I do want to do some other ones here. Questions 8, 8, 7. I really just want to do this with a calculator, honestly. I think there's one learning goal I want to point out for this one, and that is that pi can factor out. The red highlighter making an appearance there. What do you think about that, huh? The pi can just factor out. Since it's a constant that's being multiplied by both those things, you can pull it out in front and put it in front of the integral, which I'm going to do. I'm going to do pi times the integral from -1 to 1. I'm going to be really careful about this, though. This would still be big square bracket. In the first parentheses would be negative 2x squared plus 2 squared. And the second bracket would have to be negative minus negative x squared plus 1 squared dx. Like that. And I'm just going to go on the calculator for this. So I think you should too. This is what we'll do for the rest of chapter 8. This is setting up what the integrals look like when we start doing three-dimensional revolutions. So we're going to put a pi in front. We're going to have a big old integral. Or actually, you know what? Let's forget about pi, because we'll probably get like a decimal answer for this that's probably something reasonable, and we'll just stick pi on it. We're going to go integral from -1 to 1. And our first parenthesis is going to be, whoops, not you, negative 2x squared plus 2, close parenthesis squared, minus, open parentheses, negative x squared plus 1, close parenthesis squared, dx. I think I got that right. 3.2, you know, if you convert that to a fraction, you get 16/5. And so it's going to be 16 pi over 5. Now, could we have been expected to do that by hand? Sure. Would we be expected to do it by hand? No, not on the AP Calculus test. So, 8, 8, I'm going to do at least one of these before my time will cut off and my third hour class will show up, and we'll do the rest in another video. 8, 8, no calculator, so evaluate the following integrals. Let's do A, maybe off to the side. I'm going to need some room for some of these. These are calculator free. We're not going to do D also. I think we talked about that in class. I'm going to look up the actual problem so I can switch screens here. This is the this is an easy one. This is the integral of the derivative of e to the 3x times sine of 5x dx. I mean, honestly, the integral and the derivative cancel each other out. So the answer here is e to the 3x times the sine of 5x plus c. You do need a plus c on there, though, because of the way the order of operations is going to work out. I don't know what the derivative of e to the 3x sine of 5x is, but if I were to take the integral of it, the antiderivative of it, I'd be right back to where I was. But if I put a plus c on there, it still works. So you got to put a plus c so that your answer still checks out. For question B, we have an integral. We have a definite integral from 3 to 5 of e to the 4x plus 2 power dx. So the first thing we got to do is think about what the antiderivative of e to the 4x plus 2 is. Kind of an anti-chain rule problem. But this one's pretty straightforward. I mean, first of all, we need e to the 4x plus 2 because the derivative of e to the x is e to the x. But if we took the derivative of this, we would have to remember that there would be a times 4 that would kick out because of the chain rule. So our antiderivative needs to account for this. So let's divide it by 4. And that way, we'll kind of set a trap for that 4 that'll pop out. So I think this is our antiderivative. We're going to evaluate this for the values 5 to 3. So we're going to go, and don't panic too much because we're just going to leave it probably as is. We have e to the 4 times 5 plus 2 over 4 minus e to the 4 times 3 plus 2 over 4. And so this is going to be e to the 22nd power over 4 minus e to the 10th power over 4. And I guess you could consolidate e to the 22nd minus e to the 10th over 4, but that's as far as it's going to go. We don't really need to worry about anything beyond that for this problem. We got time for one more. Let's go. One more. Question C. We got the integral. No, don't let this one fool you either. This is the secant. Whoops, I got to write it right quickly though. Secant of x times the sine of x over the cosine of x dx. Now, when you see trigonometry inside of an integral, you're looking out for one of the main trig derivatives or antiderivatives that we want. So you might not see it at first, but I'm going to highlight the sine and the cosine because this is the same problem as the integral of the secant of x times the tangent of x dx, since the tangent is equal to the sine over the cosine. And if you have memorized your trig derivatives, you know that that is just the derivative of secant. The derivative of secant is secant tangent. So this is e equal to the secant of x plus c. And that's it. That's all I have to say about that one. You know, we're skipping D, so I might as well do this last problem with you because my third hour will be rolling in and it'll be fun for them to see a problem like this. This is the integral from 0 to 2 of x times 4x minus 2 squared dx. So again, all we got to really think about is how this is going to work out. I think this one is pretty reasonable to do by just expanding it, honestly. I mean, you could do a u substitution here if you want to. Or actually, no, I don't think you can because nothing will match up. So we're just going to expand it. Let's just do some kind of algebra 2 level stuff here. 4x minus 2 squared is going to be 16x squared minus 16x plus 4. And all I'm really doing there is doing 4x minus 2 times 4x minus 2. Kind of in my head really fast, but that's where I got all those parts from. The 16 comes from the fact there's going to be 2 pairs of negative 8x in there. And we still need to distribute that x all the way through. So this is the integral from 0 to 2 of, how about 16x to the third minus 16x squared plus 4x dx. And so from now what we're going to do is we're going to take the antiderivative of all of these terms there. You could, I suppose, factor a 4 out if you wanted to, but you wouldn't need to. This is 16x to the fourth over 4 minus 16x to the third over 3 plus 4x squared over 2. And we're going to evaluate that from 2 to 0, which is nice because if we plug in 0 to any of those, they all become 0. So we really just need to plug in 2 and call it a day. We're going to clean it up a little bit, though, because 16 over 4 is 4x to the fourth. 16 thirds is just going to be 16 thirds. I can't do anything about that. And 4 over 2 is just 2. So we're going to plug in 2, and we'll get 4 times 2 to the fourth minus 16 thirds times 2 to the third power plus 2 times 2 squared. And we're just going to kind of, hopefully something shakes out in this one. We can get a nice kind of easy answer. 2 to the fourth is 16. 16 times 4 is 64. This is 16 times 8 over 3, and I was hoping that something would shake out nicely there, but I don't think it will. And that's 2 times 2 times 2, and that's 8 right there. So 64 plus 8 gives us the 72. You know what? I'm going to cheat and go to the calculator for a minute. 16 times 8 divided by 3 is not anything nice, which is not fun for us. But so it's going to be 128 over 3. 72 times 3 is going to give us 216. So this is 216 over 3 minus 2, 128 over 3. So my final answer for this problem, I had to cheat with the calculator. 88 over 3 is what I'm getting for this. And that's my final word I'm saying. So I'll put a pause on this right now because as you can see, my third hour has entered the class. So we will do in the next video, when I get a chance to sit down and record anything, which will probably be later today, we'll do 8, 9, and we'll look at 8, 10, and 11. Actually, no, we're not. What did I say we're not going to do? We're not doing 8, 9. So we'll do 8, 10, and 8, 11 in another video, and I'll see you in that one. You guys are great. Keep it up.